Welcome. In this video, we'll complete our discussion of RDBMS Introduction. Recall in the last video, we mentioned SQL had three functions or categories of operations: data definition, data control, and data manipulation. In our last discussion, we talked briefly about data definition and data manipulation. Today, we'll start by discussing data control. We'll give a brief overview of this topic, and then we'll go into data integrity in great detail. So let's get started. Database users and security involve three things: identification, authentication, and authorization. After a user account has been established in the database, we've achieved the idea of identification. We've defined a username to the database. That user must then be able to prove that claim to this identity. When a user attempts to log in, they might say, "Oh, I'm the user Mo." Well, we have to prove that in some way. That's where authentication comes in. In this example, we're creating a user Mo. That's the identity. We're telling the system that this user Mo would be authenticated with a password which happens to consist of the uppercase letters STOOGE, the word stooge. Oracle, like most commercial relational databases today, supports case-sensitive passwords. Here we've chosen just to use all uppercase. After we talk about authentication and the user has now proved who they claim to be, the next is authorization, where the user will have certain privileges or permissions that have been given to that user, and this will determine what operations the user is allowed to perform. The statement that we're showing here addresses only the identification and authentication. We'll talk about authorization in just a moment. The database username that has been assigned and the password and the privileges or authorizations are all remembered by the system. They are recorded in the system catalog. That's another form of metadata. Note that simply by creating the user and saying, here's how they can prove who they are, that is, say a password is used for authentication, this does not mean that the user can actually get into the system and perform operations. What we need to do is to give users permissions, and this is accomplished with the grant statement. For example, we can allow Mo to connect to the database and perform various operations. This would be accomplished by granting Mo the create session system privilege. Now Mo can actually connect to the database. What can Mo do? Well, assume that I created the pets table as shown earlier. I can allow Mo to access my pets table. I can give him the ability to select and insert. That would mean he can retrieve rows from the table. He could also add new rows from the table. Remember, other operations that we talked about would be updating rows in a table, or perhaps deleting or removing a row from the table. I've not given Mo those permissions or privileges. Thus, what we're looking at is a type of security or authorization or access control referred to as discretionary access control. It is at the discretion of the owner of the database object as to what other users are permitted to do with that object, if anything at all. Perhaps in the future, we want to take away some of the privileges that Mo has been given because he no longer requires these. We accomplish this with a revoke statement. We could revoke create session, and that would remove the ability for Mo to connect to the database at all. Alternatively, we could be more selective and revoke only certain object type of privileges. So I could revoke the insert privilege on the pets table from Mo. Had I given him previously select and insert, he would retain the select and still be able to retrieve data from that table. There are three categories of data integrity when talking about a database system: entity integrity, referential integrity, and user-defined integrity. We'll talk about entity integrity and referential integrity in some detail. User-defined integrity essentially means that you have some kind of specific business rules that apply to the organization. Entity and referential integrity are more generalized concepts and have been defined as part of the integrity component of the relational model or the relational theory. To support database integrity, a relational database system allows the use of primary keys for entity integrity, foreign keys to support referential integrity, and there are a variety of different techniques, such as check constraints, that can be used to implement user-defined integrity. In general, there are two approaches that can be taken for a relational database system to support integrity. There's declarative integrity and there's referential integrity. With declarative integrity, we look at extensions to the data definition statements, say the create table statements, that defines some kind of a constraint as part of a business rule that will be enforced automatically by the system. With procedural integrity, it's a programmatic type of implementation of integrity, typically implemented through what is called a database trigger. A trigger is a special kind of a stored procedure that is associated with a table and also with activity against the table, so that when an operation is performed against the table, such as an insert or an update or a delete, this automatically causes the trigger to execute. The trigger is said to fire in response to the event. We'll take a look at this later in the course, and we'll use a special language that Oracle provides called PLSQL. We'll talk a little bit about that language and how we can create triggers to implement procedural integrity. The alternative to using a trigger would be to embed logic within an application program to enforce business rules. The potential drawback to this is that logic and that enforcement is contained within the application that is written. And only when that application is active or executing will that logic apply. But by creating this as a database object, which is what a trigger is, we can ensure that there will be consistency in the enforcement of the business rule when we do it procedurally or programmatically. A database design reflects a model of some application domain, some aspect of the real world. This model contains entities, which are things of interest to us. These could be persons, places, things in general. They could be events. So an entity is distinct and identifiable. We can tell two people apart. We can tell two places apart, and so on. In relational database, an entity instance is typically represented by a row and a table. We've made this point a number of times already. Entity integrity is enforced through the primary key designated for that table. The primary key has two very important properties that we wish to bring to your attention here. It must be unique, and this is determined by the values within the column or collection of columns that define the primary key. Thus, this is how we can guarantee row-level access or row-level uniqueness and be able to tell two individuals apart. Additionally, the key must not be null. Null represents a value that is missing or unknown. So how could you not know something and that be the means of identifying? So the idea is the primary key, whether it consists of one column or multiple columns, cannot contain null values because it plays the role of an identifier, in fact, a unique identifier. So consider a table named employee as providing a general description of employees. A row in the employee table will record information about an individual employee, for example, the employee that we've been referring to as Mo. This is the notion of an entity instance. Unfortunately, the term entity is sometimes considered to mean an instance and sometimes considered to mean the type itself. Hopefully from the context in which it's used, it will be clear whether we're talking about the entity type or the entity instance. When creating a table, we will almost always specify a primary key for that table. This is because a table effectively is an entity type, representing something in our application domain where the instances are distinguishable and uniquely identifiable. Oracle database and many other databases will automatically create a unique index to enforce the uniqueness requirement of the primary key. But note that not every relational database management system will automatically create an index for this purpose. The primary key might consist of a single column, in which case we refer to it as an atomic primary key. But it's also possible that the primary key could consist of multiple columns. Then we would refer to it as a composite. Our example here shows the department table, which has a single column that plays the role of the primary key, department ID. Notice that department ID is specified as not null, one of the two requirements we indicated for a primary key. By specifying this as the primary key, the system again will automatically create an index to enforce the uniqueness requirement. When describing this table, we can use a shorthand notation. This would consist of the name of the table and within parentheses, the names of the columns. The column or columns that make up the primary key would be underlined. Let's turn our attention to referential integrity. Referential integrity pertains to one entity making a reference to another entity. In a relational database implementation, this will involve the row of one table making a reference to a row in another table. We've discussed the department table in a bit of detail and talked about its primary key. Let's consider a human resources application domain, which would involve this department entity and the department table. What other entities would we expect to find in an application domain for human resources? Well, quite likely we would find employee, and employee would be related in some way to a department. An employee is assigned to a department, or an employee works in a department. In our database design, this might include some columns, such as dep ID, in the employee table to record the department to which an employee has been assigned. If we assume that each value in the column must match the value of the primary key in some row in the department table, then dep ID would be considered a foreign key which references the primary key of the department table. Note that a foreign key need not consist of only a single column. If the primary key is atomic, the foreign key will be atomic. If the primary key is composite, the foreign key will also be composite with an equal number of columns. Using terms that we have previously discussed, the table that contains the primary key and is being referenced or referred to by the other table is called the parent. And the table that contains the foreign key and is making the reference is called the child. Hence, this is often referred to as a parent-child relationship. In general, the values of a foreign key are constrained by the values of the reference primary key. This is the idea of integrity with respect to referential integrity. The DBMS will automatically enforce referential integrity by rejecting any update or insert statement against the child table that attempts to place a value in the foreign key which does not match a value that currently exists within the reference primary key of the parent table. When creating the table, we include a foreign key clause that informs the database management system of this integrity requirement for the table. We should also note that it is possible for a table to have more than one foreign key. There'll be a foreign key for each relationship in which the table participates. Another point about how this referential integrity is defined to the system. A foreign key includes what is called a delete rule. This informs the system on how to handle an attempted deletion of the parent of the referenced row. This delete rule can specify cascade, restrict or no action, and set null. Let's take a closer look at the delete rule by providing a couple examples. When we create a parent-child relationship, the names of the foreign key in the child and the name of the primary key in the parent do not have to be the same. However, the data type of each column and the size of each column must match exactly. Because remember that whatever is stored in the primary key potentially could be stored in the value of the foreign key of the child. So they have to agree in terms of the nature of the values that can be stored. When creating tables that capture a relationship, we must define the parent, or the table that contains the referenced primary key, first. So here's the code for creating the department table. And here's the code for creating the child, the employee table. Observe that dept.id, spelled with an underscore, is the name of the primary key in the parent. The foreign key that makes a reference to this is simply called dept.id, with the letters all running together, no underscore, so the names are different. But observe that the data types and sizes are the same. That's the requirement. We specify the primary key column by using the primary key clause after we've announced all of the columns in the table. In the case of the foreign key, we identify the column that will serve as the foreign key, and in this case, we simply say it will make a reference to the department table. Now the system will figure out, because of the metadata that it has stored when the parent table was created, which column or columns comprise the primary key in the target table. So the system is already aware that department has a primary key, and it knows the name and the data type of that. The metadata was recorded. This is why the parent table must be created first. So when creating the foreign key, we do not have to explicitly name the primary key column in the parent table. This example provides one form of the syntax for defining primary key and foreign key. There are other forms. Let's take a look at this example in action. I've connected to Oracle Live SQL. So let's begin by running some data definition statements to create our two tables. Tables have been created. Now let's populate these tables. What we'll do is we'll define a couple of departments. Entity integrity applies here. If I attempt to insert a row with the same department ID as that of a row that already exists, I'll be violating entity integrity. Let's give that a try. So let's attempt to insert a row into the department table with the department ID of an existing row. I'll highlight just this statement here and attempt to run this, and it tells me I violated a unique constraint. This is a violation of entity integrity. We cannot have two rows that are identified with the same primary key. Consider the idea of your student ID that you use at the school. You use this in the library, you use this in the cafeteria, and so forth. So they're tracking your activity, if someone else has the same ID, then that person is performing activity that could be attributed to you or vice versa. So therefore, we must have a unique identifier. And that's what we're illustrating here, how the system enforces entity integrity as a uniqueness constraint. Now, let's take a quick look at this department table's contents. And we see the two rows that we successfully inserted, Department D001 and Department D002. Now, we've got departments. Let's hire some employees. I'm attempting to hire 4 employees here. Employee number E0001, 2, 3, and 4. When we run this, we can confirm that, well, we had row 1, row 2, row 3. That would be employee 001 assigned to department 01, 02, 01. But our final attempt here tried to hire employee 4 and assign this employee to a department that does not exist. It tells us that we've violated an integrity constraint. This is a violation of referential integrity. We're trying to assign a parent to this row, but that parent doesn't exist. Let's take a look at the rows that were inserted into the employee table. And we see 3 rows for employee 1, 2, and 3, and they're assigned to one of the 2 departments that we know exists. So we have 2 employees assigned to department 1. Let's attempt to remove that department. We'll try to delete from the department table the row where the department ID is department 1. But notice we have 2 children for that parent. What's going to happen? The system rejects the deletion because the delete rule that is applied here is on delete restrict or on delete no action. Attempting to delete a parent row when that parent has existing children, the system says, no, you can't do that because the delete rule is restrict. Let's confirm this. Take a look at the department table. Both departments still exist. Let's take a look at the employee table. All 3 employees remain in the table. So that's a quick look at one aspect of entity and referential integrity. Let's look at a little bit more material, and then we'll come back and revisit the situation with a different delete rule in play. The delete rule associated with referential integrity is declared as part of the declaration of the foreign key in the child table. Note that as we saw in our previous example, it applies to the deletion of a parent row, not to the deletion of a child row. The previous example took the default, which is on delete restrict. So there was no indication explicitly of a delete rule in creating the child table. Let's look at another form of the delete rule. Again, we start off by creating the parent table and specifying the primary key. Then we create the child table and we specify the foreign key, and we add the fact that this is on delete cascade. Notice also in this example, we explicitly state the primary key column of the parent table. Previously, we had simply said foreign key dept ID references department. In this example, we're specifying that it references the department and specifically the dept ID column. But then we go on to add the delete rule, on delete cascade. On delete cascade indicates that if we attempt to delete a department which currently has employees associated with it, that is, foreign key values in the employee rows refer to this same department, then the system will not only delete the department, it will cascade and delete the employees who are assigned to that department as well. And this will all be done automatically. There's an additional option of onDelete set null, in which case the department will be deleted, but the employees who are assigned to that department will, in a sense, be reassigned. They'll continue to exist as rows in the employee table, but the value of the foreign key will become null, saying that currently they're not assigned to any department. A little bit more on the specific requirements of that when we talk about user-defined integrity and check constraints. The point that I want to get to there is that the foreign key column must be able to accept a null value. It cannot have a not null constraint defined upon it. We'll talk a little bit more about that in a moment. Well, here we are back in Oracle Live SQL. We're going to again use the department and employee tables to discuss more about the delete rule, foreign keys, and referential integrity. But because these tables already exist, I have to remove them. This is actually an important point to take into consideration as well. There's an order in which the tables have to be created. I create the parent and then the child. And because of this integrity, the referential integrity, I must delete them in the reverse order. Suppose I tried to delete the department table first. It will tell me that there's a problem. There are unique or primary keys in the table that are referenced by foreign keys. This is a parent table. It has children. So I must delete the child first. That's successful. Then I can delete its parent. Again, this is an extension to referential integrity. Now that the two tables are gone, I can create two tables with the exact same names. So here's the definitions that we just discussed. Notice that the child table has a foreign key that includes the onDelete cascade delete rule. So let's run these commands and create the two tables. Again, referential integrity is in play, but what we want to be aware of is there's a little bit of a difference now in terms of what happens when I attempt to delete a parent row. That is, I attempt to delete a row from the department table. Let's populate the tables and take a look at this in action. They observe that I'm inserting two departments, D001 and D002, as before. I'm also inserting three employees. Two of them will be assigned to department D001 and the other to department D002. Let's review the content of the tables. And we see the two departments are present. Now let's look at employees. And we see all three employees. Now, let's go ahead and try to delete department D001. Remember, there are two people that currently work there. It says one row deleted. Remember when we tried this with onDelete restrict, what happened was the system said you can't do that because there are dependencies. Here, it deleted the row from the department table. Let's confirm that. And sure enough, we now have only one row in the department table, department D002. But what about the children, the employees? Notice we now have only one employee, the person who has been assigned to department D002. The two people who were assigned to department D001 were deleted through the cascading delete rule. When we removed the department, the parent, the children, the employees, were also automatically removed. Notice that the feedback message that we had said you deleted one row, which is true because we were targeting the department table. The fact that additional rows were deleted in other tables, in the children or dependent tables, was not reflected in the feedback message. Both entity integrity and referential integrity can be considered universals. They're independent of the application domain. All application domains are going to be discussing entities and relationships, parent-child relationships. Therefore, the relational model clearly defines how entity integrity and referential integrity should be supported. Each application domain could have integrity requirements that are specific to that particular domain or specific to that particular organization. For example, we could probably go to 3 different insurance companies and see a lot of consistency in how they operate. But internally, there might be different business rules that insurance company 1 follows for internal operation that don't apply to insurance company 2 or 3. And the same could be said of the other companies. So we need some way to come up with kind of customized integrity rules. This is where we talk about user-defined integrity. Relational products support the check constraint and the unique constraint. Check allows us to validate a condition that has to be satisfied by a column in order for a row to be inserted or updated. Unique indicates that a column must be unique within the table. And again, these constraints can be more complex. They don't necessarily have to be limited to a single column. Now, unique sounds a lot like the primary key. The primary key imposes uniqueness. So why would we have another constraint for unique? Consider, for example, that you're an employee in a company. When you get hired by the company, they assign you a badge number or some internal identification number. That is a unique identifier and will likely become the primary key for the employee table. But also, when you're hired by a company, you have a social security number, which they have to record. And that also is unique, but it's not playing the role of the primary key. So there can be additional unique constraints above and beyond the uniqueness requirement of whatever column or columns constitute the primary key. There's another constraint called not null, which is actually a variation of the check constraint. We'll talk about this in some detail later on, but the idea is when we say a value must be provided, for example, if you're hired by a company, you must tell me your name. I can't leave it missing or omitted or null. I have to have your date of birth. That can't be omitted. It's a required value, so it cannot be null. The default option says that if a column value is not supplied, then this is the value that we'll use. For example, if it's something like a date that a certain event occurred, if you insert the row but don't tell me that date, I could specify that it will be the date that the row was inserted. This is all part of declarative integrity. These clauses are included within the data definition or create statement. Additionally, we can talk about procedural integrity. A database trigger provides a way to implement far more complex business rules than something like a check constraint could implement. Typically, the triggers are written in another language other than SQL. Oracle uses a language called PLSQL. Microsoft SQL Server extends their implementation of SQL and uses something called Transact SQL for this purpose. Sometimes these triggers can be written in a language such as Java. But triggers provide a way of implementing what is called procedural integrity. And the idea is these are used for complex business rules. We'll talk about this later in the course. In this lecture, we covered an overview of a commercial relational database management system. We used Oracle Database to illustrate many of the concepts. We did make reference to other systems as well. The idea being that Even though Oracle was used, the concepts we presented are fairly universal or standard among relational systems. So hopefully this gave you a feel for what a relational database is like. Let's recap what we've covered in this section. We talked about the roles of SQL: data definition, data control, data manipulation. We provided a high-level view of the relational model, the theory which underlies commercial relational systems. We provided an overview of the SQL select statement. We discussed the role of the system catalog as a metadata repository. And we talked about how a relational database management system addresses data integrity primarily through declarative constraints. The idea of entity integrity and referential integrity were stressed and examples were provided. We also talked about additional declarative integrity and suggested that procedural integrity is also available. That pretty much wraps up this lecture topic. Look forward to seeing you again soon.